through the fascinating evolution of control engineering. Our mission is to show you how computational intelligence and cutting-edge optimization methods are not just improving, but fundamentally revolutionizing how complex systems are managed.
Exactly. And for this deep dive, we've pulled together some really fascinating insights into modern control theory and its incredibly diverse applications. We want to show you how intelligent control techniques are moving far beyond the traditional sort of rule-based methods to tackle the truly complex, often unpredictable challenges of the real world. You'll hear about some surprising new capabilities that are already shaping everything around us.
Okay, so let's ground ourselves first. What exactly is control engineering? Our sources describe it as the engineering discipline dedicated to automatic control. And apparently it's been rapidly expanding for decades,
Right.
thanks to, tech leaps and affordability. Think about it. Almost every engineering activity, from a simple thermostat switch to incredibly complex industrial processes with multiple inputs and outputs, relies on automatic control. It's truly pervasive.
It really is. And to grasp the leap we're making now, it's helpful to understand the foundational ideas. At their simplest, control systems come in two main types: open loop and closed loop. An open loop system is, well, it's like a simple timer on an oven. It just takes an input, applies control signal, and that's it. Doesn't check if the output is actually what you wanted.
Right. Set it and forget it.
Exactly. But a closed loop system, that's much smarter. It uses feedback. It measures the system's actual output, compares it to what it should be, the set point, and then adjusts the control signal based on that error. It's constantly self-correcting.
Okay, that makes sense. The feedback loop.
Precisely. Now, the true workhorse of these closed-loop systems for a very, very long time was the proportional integral derivative controller. You'll see it called PID. A decade ago, it was the hidden brain behind over 90% of practical control systems.
90%, wow.
Yeah. But here's the crucial insight. The real world is messy, right? PID controllers, while robust in many ways, often struggle with systems that have unpredictable nonlinearities or strict operational constraints. Things PID wasn't really designed for, and there's no single PID tuning method that works perfectly for all situations.
Okay, so one size doesn't fit all, basically.
Not when things get complex. This fundamental limitation really pushed engineers to seek new, more adaptive approaches. And when we design these systems, two critical properties we always aim for are robustness, meaning the system behaves as desired even if our mathematical model isn't perfectly accurate.
Which it rarely is, I imagine.
Exactly. And the other is stability. Stability is paramount. It ensures that for any normal, expected input, a bounded input, the system will always give a predictable, controlled output, a bounded output. We call that BIBO stable. Basically, it won't suddenly go wild or produce nonsensical results. Engineers use rigorous mathematical tools, often visualized in complex diagrams like Bode plots or root locus plots, to guarantee the stability, especially in safety-critical applications.
That's a great point. The sheer complexity of the real world, with its unpredictable variables and nonlinear behaviors, really pushed traditional control to its limits.
Yeah.
So given those limitations, what was the next major leap? You said this is where it gets really interesting.
It does. To overcome those challenges, researchers began developing new structures and tuning techniques, moving us squarely into the realm of intelligent control. Our deep dive highlights 4 main techniques that are leading the charge: metaheuristics control tuning, fuzzy logic control, neural networks, and multi-agent systems.
Okay, let's start with the first one. Metaheuristics. Sounds complex.
It sounds complex, but the core idea is pretty intuitive. These are incredibly powerful optimization algorithms, often inspired by nature or even human social behavior. Think of them as smart search strategies. They're designed to find really good solutions to incredibly complex problems, even if finding the absolute perfect solution is impossible or it just takes way too long.
Okay, like shortcuts to good answers.
Kind of, yeah. Smart shortcuts. Take Taboo Search, for instance. Imagine you're trying to find the lowest point in a vast, bumpy landscape. You might easily get stuck in a small dip, a local minimum that feels like the lowest point nearby. Taboo Search cleverly uses memory. It remembers where it's been, and sometimes it intentionally moves away from an immediately good-looking solution, exploring other areas to avoid getting trapped. It helps find a truly better overall solution, not just the local best.
Interesting. So it avoids getting stuck in a rut.
Precisely. Then there's simulated annealing. This one's inspired by metallurgy, actually, the physical process of annealing, where materials are slowly cooled to reach their most stable, low-energy state. This algorithm applies that probabilistic method it explores broadly at first, then gradually cools down or focuses the search to settle on optimal solutions.
Huh. Neat analogy.
It is. And perhaps the most famous are genetic algorithms, or GAs. These truly mimic biological evolution. They use terms like chromosome, gene, crossover, and mutation. They generate many potential solutions, like a population, then they breed the best ones, combining parts of good solutions that's crossover and introducing small, random changes, mutations to create new, potentially even better solutions over many generations.
Now, simulating evolution to solve engineering problems.
Exactly. Now, what's crucial for all these optimization algorithms is finding the right balance. There's a tension between diversification, which means exploring completely new regions in the search space, and intensification, which means digging deeper, refining the search in areas that already look promising. Getting that balance right is key to finding effective solutions efficiently.
Okay. That makes sense. Need to explore and exploit. So how do these powerful optimization techniques get applied to make the controllers themselves smarter? Because that's where the rubber meets the road, right?
Absolutely. This is where we get into optimal controller parameter tuning. Instead of a human engineer manually tweaking knobs trying to find the best settings, these advanced multi-objective optimization algorithms, like an SGA2 or SPI2 mentioned in the sources, are used to automatically adjust controller parameters.
So the algorithm does the tuning.
Right. The algorithm seeks out the optimal settings to achieve the desired system performance. Things like minimizing the steady-state error, reducing overshoot, speeding up the rise time, shortening the settling time, all those performance metrics. Our sources highlight some fascinating benchmark problems they use to test these. Like the ball and beam system, that's a classic challenge. You have to balance a ball precisely on a moving beam.
Oh yeah, I've seen videos of those. Tricky.
Very tricky. Or the stirring tank with heat exchanger, where the goal is to precisely maintain a fixed temperature inside a tank, dealing with inflows and outflows. These intelligent algorithms are designed to find those perfect controller settings, even for such intricate and dynamic problems where a simple PID might struggle.
Okay, so we've seen how algorithms can fine-tune a system, finding the best settings for a controller that's already sort of defined. But what about systems that need to truly reason with imprecise information? Or maybe even learn entirely new control strategies on their own? That sounds like it brings us to fuzzy logic and artificial neural networks. How do these intelligent approaches actually work and, where are they making a real difference?
That's a great distinction. Fuzzy logic control, or FLC, is fascinating. It allows systems to reason with imprecise or uncertain information, much like humans do. Instead of rigid yes or no, black or white decisions, think of it like giving a computer a sense of maybe or somewhat.
Handling the gray areas.
Exactly. Its core process is called fuzzification. It converts a crisp numerical quantity, like a specific temperature reading, say 21.5 degrees, into a fuzzy one. This fuzzy value is represented by membership functions, which basically say how much that crisp value belongs to concepts like cool, warm, or hot. This lets the system interpret things like slightly warm or very fast, handling the inherent uncertainty or vagueness in real-world data. Systems like Sujuno controllers can even be trained using data.
So it makes computers think a bit more like people in terms of language and concepts?
In a way, yes. It makes them more adaptable to the kind of subjective, imprecise information we deal with constantly. Then you have artificial neural networks, or ANNs. These are a machine learning approach that attempts to simulate the function of the human central nervous system, particularly the brain. They're designed to learn from data, much like our brains learn from experience. They consist of interconnected neurons.
Learning machines, essentially.
Right. Key properties include tuning, where specific neurons or groups of neurons become responsive to particular patterns or features in the input data. There's plasticity, which is crucial. It means the network can be trained. Its internal connections, the parameters, can self-adjust based on experience or training data. And perhaps most powerfully, there's generalization. This is the ability to provide sensible outputs for inputs it hasn't seen before based on what it learned from the training data. It can solve problems it wasn't explicitly programmed for.
That sounds incredibly powerful, learning and adapting.
It is, and what's particularly potent is when you combine these techniques. We talked about adaptive neuro-fuzzy inference systems, or ANFIS. Our sources make a strong case here. They mention a specific type, a neuro-fuzzy logic controller using a genetic algorithm, NFLCGA, and note it demonstrated that the NFL-CGA provides better performance and is easier to design than a conventional fuzzy controller and a PID controller.
Better performance and easier to design. That sounds like a win-win.
It really highlights the power of hybrid approaches, leveraging the strengths of neural learning, fuzzy reasoning, and genetic optimization all together.
So, okay, this is all very advanced stuff. What does it actually mean for real-world impact? This isn't just sitting in research labs, is it?
Oh, far from it. These technologies are making a tangible difference right now across many fields. For example, in smart structures. Think buildings or bridges. Fuzzy techniques, combined with an understanding of how materials degrade over time, continuum damage mechanics, can proactively identify damage. And these systems are incredibly robust, performing well even under conditions of noise or high uncertainty. Imagine buildings that can sense their own structural integrity.
Wow, infrastructure that diagnoses itself.
Exactly. They're also used in manufacturing, predicting problems like delamination, that's layers separating when drilling advanced materials like glass fiber reinforced composites, crucial for quality control and safety. And perhaps most visibly to many of us, you see these intelligent systems providing guidance, control, and even fault identification in advanced automotive and unmanned vehicles, making cars, drones, and robots much smarter and safer.
Right, self-driving cars and the like.
That's a big one. And a really significant point our sources emphasize is that NFIS controllers, these hybrid systems, can achieve things like satisfactory vibration suppression, keeping things stable comparable to classic control methods, but without needing complete knowledge of the system's internal state. They don't need a perfect mathematical model of everything. They just need a set of appropriate data for the learning procedure.
That's huge, because in the real world, you often don't have perfect information, right?
Exactly. It makes these intelligent approaches much more practical for messy, real-world problems.
That really is a major shift systems that can operate effectively, even with incomplete information. The ingenuity here is incredible. And the cool thing is, these intelligent control methods aren't just theoretical. They are popping up and making a tangible impact in the most surprising and diverse places, truly transforming industries and daily life.
Absolutely. Let's walk through some compelling applications mentioned in our sources. Consider water desalination, specifically seawater reverse osmosis, or SWRO. A major challenge here is something called concentration polarization, where salt builds up on the membrane surface, reducing efficiency. Now, computational intelligence, or CI techniques, are being efficiently used in systems with complex dynamics, like these SWRO plants.
Okay, how so?
Well, imagine an SWRO plant powered by variable renewable energy, like wind power. The power supply fluctuates, right? CI techniques allow engineers to replace the PID controllers with controllers which use multiple input variables. These intelligent controllers can adapt to the uncertain power supply, optimizing the desalination process continuously, making clean water production more reliable and sustainable even with renewables.
That's fantastic, adapting to green energy sources. What else?
Or take healthcare. This is a really impactful area. Neural networks are being applied to develop much smarter blood glucose control devices, particularly for people with type 1 diabetes, T1D. This is incredibly challenging because of the nonlinear insulin absorption pattern. How the body uses insulin isn't simple or predictable, and the critical need to tailor insulin regimen to individual patients' need. Intelligent control offers the promise of highly personalized adaptive systems like an artificial pancreas that could dramatically improve quality of life.
Wow, truly personalized medicine driven by AI.
Then there are large-scale systems like energy grids. We're moving towards cyber-physical human systems, CPHS. Think smart grids. Here, techniques like cooperative control and distributed optimization are used to manage these incredibly complex digital power grids and smaller microgrids. One benefit is mitigating problems like low-frequency oscillation, which can destabilize the grid. Interestingly, humans are also part of the system acting as players or agents in an electricity market, where game theory concepts like seeking a Nash equilibrium come into play to balance supply and demand efficiently.
Humans as agents in the control loop. Fascinating.
It is. Now let's talk traffic management. We mentioned autonomous vehicles, AVs. They're being designed with sophisticated feedback control algorithms that can do more than just drive the car. They can actually dissipate stop-and-go waves caused by human driving habits. You know, that frustrating accordion effect on highways.
Oh, I know it well. You're saying AVs can smooth that out.
Yes. Our sources cite both numerical simulations and actual field experiments showing an astonishing result. Approximately a 20% fuel consumption reduction across all vehicles in the traffic flow just by having one AV strategically controlling the pace.
20%, just from one smart car in the mix.
Apparently so. It smooths the flow for everyone. That's a significant environmental and economic impact, potentially. And closer to home, smart homes. There's a concept called non-intrusive load monitoring, or NIM. This aims to capture detailed energy consumption of electrical appliances using just a single smart meter for the whole house rather than metering every single device.
How does it know what's using power?
By analyzing the electrical signature of different appliances turning on and off, the challenge is distinguishing them accurately. One source shared a surprising fact from a case study. A television was the device with the highest cumulative consumption. Why? Because it was left on just background listening to radio stations through the TV.
Huh. Oh, you'd expect.
Right. But it also highlights the challenges. Things like an electric oven can be tricky. Its power usage varies a lot, leading to false positive events where the system might mistakenly attribute power peaks to the oven when it was actually something else. Getting that recognition right is key.
I see. Still needs refinement.
Definitely. Then there's high-tech manufacturing. Think the semiconductor industry. Our sources call it the most capital-intensive and most composite manufacturing environment. Extremely complex. Here, run-to-run, or R2R, control is absolutely critical in wafer fabrication. This involves making tiny adjustments between processing runs of silicon wafers to maintain incredibly high quality and minimize defects, especially in critical steps like photolithography. Advanced techniques, including reinforcement learning, RL-based methods, are being used to handle uncontrollable noise and process delay, often outperforming traditional statistical methods like EWMA controllers.
Keeping those microchips perfect.
It's essential. And one last example, public transport, specifically hybrid electric buses, HEBs. A methodology called fleet learning is being applied to reduce operation and maintenance costs. The system analyzes data not just from one bus, but from the entire fleet. It learns from the buses exhibiting the best energetic behavior, the most fuel-efficient driving patterns and energy management. Then it uses decision-making processes to essentially teach or guide the less efficient buses or their driver systems to improve. They reported an energetic improvement on the fleet up to 18.7%.
So the buses learn from each other effectively. That's clever.
Yeah, leveraging the collective data of the whole fleet to make every part better.
It's truly incredible how widely these intelligent control methods are being applied, transforming everything from, how we get our water to how we travel, manage energy, and even how microchips are made. What stands out to you the most about how these smart systems are shaping our daily lives and industries?
Well, I think what's most fascinating here is the profound shift it represents. We've genuinely moved from basic reactive feedback loops, simple thermostat logic, if you will, to these incredibly sophisticated, intelligent, and truly adaptive control systems. They don't just automate tasks anymore. They learn, they predict, they optimize, often in staggeringly complex and uncertain environments where the old methods would just fail. And this relentless drive for balance, you see it everywhere, whether it's that balance between exploration and exploitation in the optimization algorithms, or balancing individual needs versus collective goals in large-scale systems like power grids or traffic flow. It isn't just an engineering marvel, though it certainly is that. It feels more like a fundamental quest for efficiency and resilience, a quest that's touching almost every facet of our technological world.
The quest for efficiency and resilience. Yeah, that really is the thread tying all of this together, isn't it? It definitely makes you wonder how much more intelligent, how much more optimized our world can actually become. And thanks for joining us on this deep dive into the fascinating future of control.